Good morning again. Last week, we talked about the internal force diagrams and their applications. We solved a few problems and remind how to draw the internal force diagrams. We have three internal forces: axial force, shear force, and moment. We know how to draw diagram. Now, from now on, we're going to start to examine all these internal forces one by one. Today, we're going to talk about the axial force effect on the section. Now we know how to draw the axial force diagram. Okay. We know the distribution, the normal or axial force on the structural system. So how can we evaluate this axial force effect on the structural system, or how can we check the stresses due to axial force? Today we will learn this part. Let me share my screen first. Yes, I guess you see my screen, whiteboard. Okay. Here we go. Axial force effects. Okay. When we see this effect, if a structural member is under only axial force effect, for example, I have a column. Like this. There is only axial force on this member. So this is an example. Or I may have a column which change its section somewhere else over here. This is another type of column. Or we may see cables. If you remember the statics course, we learned to calculate cables. Cables have only axial forces. These are the examples where we see only axial force effect. Okay. Another example, arch system. Okay, in cables, yes, we have axial force, but we have only tension force, If we have an arch, under this loading, again, we have only axial force on the arch, but this is compression. By the way, let me remind the axial force again. Axial force here. And we have tension force and compression force. If we have a compression force, as you know, if we squeeze the structural member, squeeze it, we apply compression. So the force is always goes into the structural member. If we apply tension, if we apply an axial force to out of the member. We are gonna make our structural member straight. So there will be tension on that member. So the force always goes out from my structural member in tension effect. Okay, in tension effect. So these are the some basic examples which are under the axial force effect. Now we know the two types of axial force, tension and compression. So while we are designing the structural members, now we are going to learn how to design the structural members under axial force effect today. So while we are doing this, we check the stress. The first thing is first, we check the stress. Stress means, so it's a kind of strength. Okay, we check the strength, we check the deformation. How we check the strength? We calculate the stresses under this loading condition. If my calculated stress is less than allowable stress, remember what the allowable stress is. The allowable stress is the maximum stress we can reach to, okay, on a structural system. If our stress is less than that top limit, okay, our structural member works well under that axial force condition. Also, when we apply an axial force, let me write for design. We're gonna do strength check. Okay, we've just talked this one, and we're gonna check the formation. Actually, under axial force effect, the members change their lengths. We will talk about that. For example, when I apply a column, if this is an axial force like this, we know that its length will be changed to this level. For example, from here to here, there will be a length change. Another example, for example, while you are carrying some package, let's say, you don't feel these chains. If you carry something over here, you have a package, and package here, it's heavy. It has an effect in this direction. So it a little bit elongates your arms. You don't feel that. It's an elastic length change when you put your luggage on the ground and it goes back. But in theoretically, every axial force member change its length. Okay, we will talk about in the next stage about this. Let's get started to the stress calculation. Okay. Here we go. Okay. Let's say we have a member under axial force. Let me draw it here. Okay. Okay, we have a member under axial force. And here looks like this is this is okay. Okay, if we have a section at mid portion of this frame member, I'm gonna cut the system from this red section and draw it down over here. Let me draw it again here. So we have an axial force over here. This is the surface. This portion is the surface where we cut the system. So there's an area here. Change the color. Here we have an area, and we have some small forces for all unit area. Okay. How do we call this force? It's like stress. Okay. Stress was a force per unit area. Okay, remember this definition. And also remember this sigma. Sigma shows us the axial stress. It's like a capital G, but goes up like this. So if you write the equilibrium equation here, the axial force from the equilibrium equation means when I cut the system from this mid portion, system is in balanced position. There is no an unbalanced situation. So if there is a balanced position, you can write the equilibrium equation. That means the force at the left-hand side, total force at the left-hand side equals the total force at the right-hand side. Okay. So and at the left-hand side equals the total force here is stress times area. Okay. Stress times area. Here, to use this rule, you know, here when we apply a load to structural member, there will be a deformation on the system. But we are going to use the rule which is planar sections remain planar after deformation. This rule is important if we say this rule in Turkish. Düzlem kesitler düzlem kalır. Yani deformasyon şekil değiştirmeden sonra düzlem kalır. Okay, this is the Turkish wording of this rule. Why this is important for us? If we have a planar section, after that, after the deformation mainly, it remains planar. That means our stress distribution will be uniform. Okay. This is important to make our calculations. Okay. If the stress distribution is uniform, that's okay. We can write this equation easily because we know that the stress is everywhere and the magnitude is same. So stress times area gives me the force on the section. Okay, so this rule helps us to make this calculation. We will see this rule in the next stage in different areas. And when we use this rule, we can do our hand calculations easily. Otherwise, it's not easy to make these calculations by hand. Yes, we can do it, but it takes time. Okay. Now, we know what the axial force is. If the force is tension, stress is tension stress. If it's compression, compression stress. While I'm defining these forces, tension or compression, some materials have different allowable stresses for tension and compression. So we can say, oh, it's an axial force. Who cares the type of the force? Yes, we care, because we will check these calculated stresses with the allowable stress. So for some materials, tension capacity, tension allowable stress, and compression allowable stress is completely different. That's why we have to evaluate these stresses according to their type. Okay, that's why it's important. Okay, let's jump to another page. Okay, we can write this force and stress equation, N equals stress times area equation for an arbitrary shaped prismatic member. Let's draw it here. If we have an arbitrary shape like this, okay, so we have those like that. This is y-axis. This is the x. Okay, this is an arbitrary shaped member. If we have here, for example, a small area on the member, this red area, let's say what we have, the area is here, dA. It's a small area. Okay. This section is under the axial force effect. So, what is the axial force on this dA, on the red area? we can write here what we have, the stress times area. So stress is the stress. It's same all over the area. So the area of the red portion is dA. So sigma times dA gives us the force. So we can write the equation axial force is total stress times dA. For each small portion, if we calculate sigma times dA, and at the end, if we sum all these numbers, we can get the axial force here. And here, in this equation, the constant number is this. Why this is constant? It's same at each point of this surface. Okay, we can take this out over here, and equals sigma times total by the way, instead this dA, I can write just a second and then change this function. That's right. Delta A, total area, and from this portion is basically area, right? So, and it's here sigma times A for any type of planar section. Okay. In the previous example, when we did this calculation, it was for the rectangular section, but now we have an arbitrary section. But at the end of the day, the calculation is same. The axial stress is proportional with the area. Okay, don't forget this one. It's proportional with the area. Stress is always stress. It's constant at each portion. So the stress times area gives us the axial force, and or we can do this N over A if you like to check the axial stress. So this axial stress should be less than design. The axial stress should be less or equal to axial allowable. Okay, allowable stress. This depends on the on the material. You don't have to know this allowable stress. If you need to use that in the calculation, we always give it to you. Okay. Yes. Basic question for you. If I have a column like this, okay, here I have the section here is rectangle, okay, for each portion, top, smaller portion, and the large portion. And if I check the stress on the section 1, and the section 2, where I get the maximum stress. Do you have any idea? If I'm asking you maximum, please calculate the maximum axial stress under this loading. Where do you look for the axial stress? On section 1, section 2. Any comment? Or are you looking? Okay, you know, axial force is axial force at each area. So we know that sigma equals axial force over area. So what we are looking for? We are looking for the maximum stress. So if the area goes down, if we have less area, this is constant in this example, maximum stress gets maximum value. So I try to find the maximum stress on the minimum area. Okay, the minimum area. So on the 1-1 section. Okay. Now, actually, the axial stress concept is this. Now, I'm gonna talk about a little bit elongation. Elongation. What is it? How we get the formation. I will explain it to you. Let me write it over here. Okay, now we're going to talk about the elongation under axial force effect. Okay, axial force effect. What is this, by the way? What is this? Let's go. Now, here we have a number. Let's see. So we apply axial force to this number. Okay. And at the end of the day, under this loading condition, what I get let me change the color. And at the beginning, my length was L. This is my initial length. So when I apply this N, what I get is L till here, and there's an increase on the length, okay, which is delta L, okay, which is delta L. So elongation is the which is the length change, okay, ratio. Let me, this is the elongation, and the strain is the length change over initial length. Okay, initial length. This is the gives us the strain on the member. By the way, remember the first week we talked about the hook member. What was it? Hook member. There was it was about the stress and strain. This is the stress. This is the Hooke's rule. What we see here, there is a linear relationship between stress. This is the stress. This is the strain. Because we are doing all these calculations in the elastic region of the material. If we remember, kept the steel stress strain diagram, it was like this, right? This is sigma, this is epsilon. We are dealing with this portion. Okay, we are in this portion. Here is elastic region. Okay. By the way, linear elastic region, that's better. Linear elastic. So this here, the slope of this linear part is E, which is the modulus of elasticity. Okay. So this is a constant number. Constant. Depend on the material. Okay. Constant number. Okay. We know what it is. So how we can calculate the this length change. What I'm trying to do, I'm trying to calculate this delta L. What is this? Okay, what is this? Let me write the equation here. Equals E times epsilon. So what was the sigma, the stress? It's N over A, right? If you take a look here, sigma equals N over A equals E. E is E. And what is the epsilon strain over here? Strain. Şekil değiştirme. As we define this portion, delta L over L. Okay. Now, I'm looking for delta L. If we write the equation like this, take this other side and make the arrangements on the equation. Delta L, by the way, the delta L is elongation. Okay. Uzama. This is the equation of elongation you have to know. Okay. This equation comes from the Hooke's rule. In the Hooke's equation, we put the N over A instead the sigma, and then we put the delta L over L instead the epsilon, E is E, it's constant. It depends on the material. As you know, it's a modulus of elasticity. So if we make arrangement on the equation, we're gonna get delta L equals NL over EA. Okay, NL over EA. This is the second equation that you have to know today in this subject. So N is here in this equation axial force, right? Let's write all these unknowns again. This is axial force. Axial force. L, what is L? The initial length of the number. E is modulus of elasticity. And A is area. Okay. The delta L, delta L is elongation. Okay. So we have two equations for today. One is regarding the axial stress N over A. Second one is this delta L or elongation, and L over EA. L over EA. Another, how we see axial stress on our structural systems. I'm just gonna give an example. Then we are gonna have a break. Today's subject is not long, it's easy and short. The subject is this. I'm just gonna draw an example. Then we're gonna do a break. Then we will solve a few examples. Then we will complete the subject today. Okay. Next week, we're gonna run a new subject. For example, if we have a wall, masonry wall, yığma bir duvarımız olsun. This is the foundation. Okay. This portion is the wall portion. This portion is foundation. Okay, wall takes the load from upper floors and transfer it to the foundation. And then, by the way, I forgot to this portion. Here is the ground. Or this is the ground. Or we can say soil. Now, the load comes from top. And this wall takes it to this surface, okay, first. So then if we cut the system from that portion, we will see Here we are going to see the stresses like this, and act from the action reaction principle, this stress acts on top of the foundation, and this is sigma 1. So when we apply this axial stress, there will be stress on this surface. So we're going to transfer the stress to the foundation. So the first rule is our wall has a small area than foundation. So firstly, our sigma 1 stress should be less than the allowable stress of the wall and also allowable stress of the foundation to make a safe design. Okay, we have a stress over there because the area is small. So the sigma 1 should be less than allowable stress of both wall and foundation. Then we take this sigma 1 on the foundation and transfer it to ground. Here, by the way, let me clear this part. And right here. Okay. Now, what I'm gonna see here on the ground, I will see sigma 2. So when I compare sigma 1 and sigma 2, because both of these stresses occurred under this axial stress N. Okay, so which one is greater or bigger than the other one? When we compare the areas, sigma 1 here, bigger magnitude than sigma 2. That's okay. We know that. But we can't say, okay, I checked sigma 1, it's okay. I don't need to check sigma 2. Why? Because sigma 2, the sigma 1 is in between wall and foundation, right? Here we have a material. And also here we have another material. This is wall, a brick wall. Here foundation is a concrete foundation. That's okay. But the relation of the sigma 2 is in between foundation and soil. Okay, that's okay. Our foundation can transfer the stress sigma 2. We know because our foundation transfer the bigger stress, which is sigma 1 greater than sigma 2 here. My foundation is okay for sigma 1 because I checked it in this portion. But don't forget this one, we have to check the soil stress, okay, on the ground. Axial stress over the foundation area gives us the sigma 2, which is the stress on the soil level. So we are gonna check it. It should be less than sigma 2, less than sigma allowable soil or soil bearing stress. Okay, soil bearing stress. Okay. Yes, that's all for the concept today. Let's have a break. Half an hour to 10:30, and we're gonna go ahead. Okay, in this second session with examples. See you guys. Okay, the first example is we have an arch like this. There is a steel member over here, and we are gonna hang a chandelier. I don't know how I can. Here it's 500 kilogram, and the total length of the cable is from here to here, 9 meters. Yeah. Another, let me see the other information. Signal logo for the steel is 1,400 square, and the E modulus of elasticity is 2.1. Okay. Okay, we have a roof. As you can see, we have a roof, and we are hanging a chandelier which has 500 kilogram with a steel member which connects to this roof. The question here is design the steel cable and calculate the elongation on the steel cable, or steel round section. Let me, instead of the cable, that's gonna be good. Steel round section, and calculate on the steel member. Okay. Steel member. So the section of this steel member is this. It's a solid steel member. To size it, what we are going to do, we are going to decide the diameter of the section. So design means determine the dimension for structural member. That means for this question, what is the, for the second portion, what is the delta L elongation? Okay. Now we will do it. So basically, the stress, while we are designing the sections, we know that what we know here, we know only allowable stress. So any stress on the section, on the member, cannot be greater than this allowable stress. The stresses can equal this one. So all the stresses should be less and equal with allowable stress. Okay. So to design this, So at the end of the day, I have a member from here to here, 9 meter. At the bottom, I have 500 kilogram axial load. So if I draw the axial force diagram of this member, I'm gonna see this positive 500 kilogram. This is the axial force diagram. Okay, I know the axial force on the member is 500 kilogram. So I'm gonna design the section N over A. To find D, I have to find the required area. Okay, required area. Okay, I'm gonna calculate this one. Then I can calculate D. It's easy. If I have the area of a circular area, I can calculate diameter of that round section. That's easy. The important part is to calculate the area. That's okay. We are gonna looking for this. Okay, N is okay, and we know 500 kilogram. What is stress? Okay, in this type questions, what we do, we know that actually we don't know the stress, but we know that our maximum stress can be allowable stress. Okay, allowable stress is our limit, which depends on the material type, and it's given in the question, as you can see, sigma allowable at the left-hand side here. So here, what we will do, we are looking for A, change the location of these two components here. A equals N over, put the sigma allowable here. Okay, because if I put here allowable stress, I can calculate an area, which is the optimum area for this section. So my stress can be maximum allowable stress. Don't forget this one. When I say you design the section, keep this in your mind. The maximum stress can be my allowable stress. Put this allowable stress instead the stress, and then calculate the area. So if I do this arrangement, the left calculations are easy. So because what are we gonna do? Area here equals N. What is N? 500. And allowable stress 1400. Okay. So from here, what I'm gonna have, okay, this is my required area. That's okay. I need this area. By the way, I can use greater area than this, but I can't use less than this area, because if I use less than this area, my calculated stress will be greater than the allowable stress. Okay, allowable stress. That's why we can't use an area less than this one, this calculated one. For example, this is 0.357 centimeters square. In real life, what we do, okay, this is the required area. Let's assume that 0.4 centimeters square, greater than this one, not less. You can't say, let's use 0.3. No, if you do it, if you check the stress, again, you're gonna see the stress will be greater than allowable stress. That's why, no, we in design, in real life design, we round up these numbers, these areas. Okay, but here we don't need to do any roundup. Okay, this is my required area. So can we do the calculation for D? Yes, the area of the round section is P diameter square over 4. equals, so if you use the P from your calculator, P is P, don't put here 3. Your calculator gives the exact number P, use that one. The only unknown is D here. If you do this equation, if you solve it, you're gonna see that D is 0.7 centimeter. Okay. It's around this one. But let me check. I guess it may be. Maybe my notes are wrong. No. Let me check it. Times 4 over T. Here D is the calculated D actually. Let me write. Centimeter. So if we round it up, you can put this number. That's okay. This is correct. If you like, you can round at the end to the closest number, 0.7 centimeter. Okay. This is the D. This is the D. Okay. So now what we are going to do now, we're going to calculate the delta L. Delta L. Let's do it in the next page. Delta L. NL over EA. Okay. Now, the area here, we know axial force. L, this is the land. E, this is the area. Let's do the area. The area is so P times calculate that. The D is so close to the area is okay. If you do this calculation, you're going to see this number. And let's write delta L and 500 kilogram. L 9 meter. By the way, in your calculations, you have to use the same units. Okay, this is kilogram. Okay, L is length of the member, 9 meter. 9 meter. E, what was E? 2.1 1 times 10 power 6. This is in kilogram centimeter square. So times area is, as you know, from above. This is in. So as you can see, our main units are in kilogram and centimeter. Let's come back to length. Length is in meter. Put here 20 and convert it to centimeter. Okay. Now all the units are in same site. So we are using kilogram centimeters in our calculation here. So the result here is 0.55 centimeter. This is the total elongation. That means when I apply this force to 9-meter member at 500 kilogram, my member will elongate a little bit. This is 0. It's almost half centimeter. That's okay. It depends on our section. So as you can see in this equation, if we increase the length of the member, our delta L increase. So and it's proportional with the N and L. But otherwise, we have EA. If we increase this portion, EA, E or A, one of them, our elongation will get reduced. Okay, will get reduced. Okay, this is the basic example. Actually, this subject is really basic. There is nothing more to do. So everything is around of these two equations. One stress equation, stress equals N over A. The other one is delta L is NL over EA. This is the second equation. If we know all these equations, I guess you memorize it. That's it. It's easy. If you understand what you are doing, you can use this one. Otherwise, it's not easy to use this equation, even if it's really basic. Let's do another example. I have second. I remember. Yes. I apply 4 times to this member, and the length of the member is 90 centimeters. Okay. Here we have what we have, by the way, allowable stress. Modulus of elasticity. Okay, for this member, for this, by the way, the section of the member is rectangular. If this is H, here is 3H. Okay. So this is the section of the member. The question is here. design the section to provide ensure an elongation of maximum 0.8 millimeter. Okay, what we have a number like this, and the section is rectangle and it's proportional 1 and 3. So design means determine the numbers for H and B. Okay. When we say design, calculate the dimensions of the number. Calculate this one and this one. Okay. Okay. Now, what we need to design this section, we have to check two things. First, we have to check the strength, and we have to check the deformation or elongation. Elongation is a kind of deformation for that member because there is a length change in the axial force direction. We are going to check the strength and deformation. So at the end of the day, for strength, we're going to calculate an area which ensure the maximum allowable stress. And then we are going to calculate an area for the maximum 0.8 millimeter elongation. Then we are going to compare. We are going to select one of them. Which one is correct? Let's do it. The first step is strength check. Okay. Strength check. So our equation is this, as you know. I'm going to select an area for the allowable stress. Remember, we use for design for this portion allowable stress. Okay. Now the area is N over allowable stress. If we change the location of these two. So let's calculate the area here. A is here, and is 4 ton. Let's have a look at the allowable stress and E, modulus of elasticity. They're all in kilogram centimeter. Okay. As you can see here, all in kilogram centimeter. So here we have ton. Let's convert this ton to kilogram. By the way, in this type of calculation, if you're going to do a unit conversion, I always check the allowable stress and E, modulus of elasticity is units. Try to work in these units. That's better for you. Okay. You don't, at that time, you don't have to convert the allowable stress and the modulus of elasticity to another unit. So if reduce the mistake potential. Okay. Here N 4 ton and 4,000 kilogram. This is in kilogram. Allowable stress here is this is okay. Now if I calculate an area from here, this 5.72 centimeters square. This is required for strand. If I use an area less than this one, I go beyond the allowable stress. So it doesn't work for me. My section will fail at that time. So this is the minimum required area. We can't use an area less than this one. You can use greater areas, that's okay. Bigger areas, that's okay. But we can't use the smaller areas than this value. Okay, this is the strand check. Let's do the elongation. Elongation check. We have a limit, right? Which is here, 0.8 meter. 0.8 meter. So we know what is delta L, and L over EA. So if we change the delta L and A's positions, A is gonna be N L over E delta L. Okay, delta L. Now A equals here, N is N, you know, 400. 4,000, sorry. 4,000 kilogram. The total length is 90 centimeters over E. E is in kilogram centimeter. It's this. Delta L. Delta L here is 0.8 millimeter. And by the way, let me show you the again units to you. Here is kilogram. Here is centimeter. This is in kilogram centimeter square. And we are going to write here 0.8 millimeter, convert it to centimeter because all other numbers in kilogram centimeter, so in centimeter. So let's write here 0.08. This is in centimeter. We have just converted the 0.8 millimeter to 0.08 centimeter. Okay. This is easy. If you do a few examples, you're gonna follow the units. But if you don't do, your solution will be completely wrong. That's why be careful regarding this issue, this unit conversion. I suggest you to use always a given allowable stress unit or modulus of elasticity unit. Okay, this is a suggestion, but you can select another unit. That's okay. Here we go. The calculated area from here is now we have two areas. What should we do to calculate the dimension of the rectangle? Which area should we use? What we have here, we have this one. This is the first area. The other one is this. So for strength check, the 5.72 works. That's okay. For the strength, that works for us. Let's have a look at the elongation. For elongation, to limit the elongation around 0.8 millimeter, we need 6.43 centimeters square. Okay, if we put an area less than this, less than 6.4, for example, if we put the first area 5.72, we can't limit the elongation at 0.8 millimeter. The elongation will be longer than our limit. So when we compare these two areas, our area, so we have to select one of these areas, but which one is correct? If we select the second area also covers the first one, because this is the minimum required area. So if I put 6.43 instead 5.7, it works. I know the stress will be less than allowable stress, that's okay. So here the area selected area is 6.43 square. So this is my required area. This area covers both calculations. Okay. Then what we are going to do? We have to design the section. We have to calculate the dimensions of the rectangular section. So the area of rectangular section is h is 3h equals 3h square. From here, 3h square equals 6.43. If we do this, the h is, let me check it, yes, 1.46 centimeter. So it's not easy to give the 1.46 centimeter. Instead, what we do, we round up this number. We round up this number to the close one. But in exam or whatever, you can use this 1.46. Okay, no problem to do that. But in real life, while we are designing structural members, there is no dimension like 1.46. Doesn't work for real life. Instead, what we do, we point here 1.5 centimeter. And if this is h, b is 3h equals 4.5 centimeter. If I use these dimensions under this loading, my stress will be less than allowable stress. Then I'm gonna limit the elongation with 0.8 millimeter. Okay, it's gonna be less than 0.8 millimeter. Yeah. Okay. Any question? Yeah. The last example is really basic again. If I have a member like this, actually I'd like to let's change the question. Low stress. Let me check. E. Yes. So I have something here. I have a square section, 5 centimeter, 5 centimeter. Here, perform the stress check and calculate the total elongation. Okay. Let's do the stress check. What we are going to do, we are going to do the, we're going to calculate the maximum stress on the structural member and then compare it with the allowable stress. Okay, that's it. Here, where we find the maximum stress, basically. By the way, if you draw the here, if you have an axial force like this, draw the axial force diagram to see in which portion you have which axial force. For example, there's a section change over this line. So in this portion, we have this axial force. Okay, in this example, we have a constant axial force. That's okay, but according to the question, it might be changed. That's why please draw the the axial force diagram and see what you have in that portion. Or the other portion is this one, and you can see here we have again 500 kilogram. Okay, in first and second portions we can perform the stress check. So let's say this is the sigma 1, the kilogram is 500 kilogram and the area is 5 times 5. Okay, let me calculate. Okay, in the first portion, sigma 2. So in second portion, I'm expecting a higher stress value than the sigma 1 because the area is smaller than the first portion. Yes, here 2 times 2. Over. Yes. Both stresses, yes, we have a higher stress than sigma 1, but both of them are less than allowable stress. Okay, now we are going to calculate the total elongation. Total elongation. Here, you have to be careful. This is really basic, but you have to be careful. If there is, you know, our delta L and L over EA. If there is a change on the axial force or area, these portions are critical portions, okay? It's really important. Here, the total L is, let's have a look at the first portion, N. N is what? Take a look at this N. In this example, the axial force is constant all the way to the support. That's okay. But in any other example, you have to be careful. You have to be careful. You have to take into account the what you have in the axial force diagram. Here, 500 times. By the way, I completely forgot to give length. I'm sorry. I'm gonna give the length now. I really don't know at the moment what. Let me write. 4 meters, and this portion is 1 meter. Okay. Total is 4 meter, 400 centimeter. E, what is E? 2.5 times A. A is here, the area of the first portion. This is the elongation of first portion, okay. Plus, add the second portion to the first one. Let's write the equation for the second. Take a look at the axial force here, again, 500. Length of the member is 1 meter converted to centimeter here. E is E. It doesn't change because it's regarding the material. It's coming from the question. Times area for. Yes, this gives us the total elongation. This is the second portion. Let me calculate the number. We are in centimeter. We're gonna have a value in centimeter again. 500. 500 times 400 over. Here the number is 0.004 approximately. And the second part, 500 times is times 4. Here is 0.006. These are in centimeter. So total is 0.01 centimeter. Okay, it's so small. I don't have any text for this question. I've just written that question at the moment now to explain different lengths or to explain the total elongation. As you can see, we consider each portion for this example. Okay, another and question. If I have an example, no, change. Here I have a 500 kilogram again, and here I have one more 500 kilogram, and the section is 2 centimeters two, and sigma allowable. I don't need the allowable stress. The question is here total elongation. E here is 2.1 times. Okay, the total length. Four meter, 2 meter. Okay. Okay. Calculate the total elongation. Firstly, we need to draw the axial force diagram. You know the rules, how to draw it. I'm not gonna do it again. And directly draw here. It will be like this. This is positive here, 500, and here 1,000. This portion again 1,000 kilogram I have. This is the end there. Okay. Okay, my section is same. There's no problem. But here there is a change on the axial force. We have to be careful while we are writing the total elongation. Yes, let's have a look to first portion. So this axial force defines the portions. Okay, in the first portion we have 1,000 kilograms, sorry, and its length is 4 meters. E is E. A here is 2 times 2, 4. Okay, plus. This is the elongation for this portion. Now I'm gonna write it for this portion plus the axial force over here is 500 in this portion. Take a look there. This portion is 500. 500 times 2 meters over times 4. And this gives us the total elongation. Let me calculate it. I don't have the result. Times here, this is 0.047 centimeters. And here is plus, here is times times 0.0 centimeter. So totally the result is 0.06 centimeter. Okay. This is the total elongation. Okay. Any questions so far?
Hocam benim bir sorum var.
Yes, no, this is really basic. We are gonna ask about this subject in the exam. Okay. This is the easiest one, easiest subject. Please don't miss this question in the exam. Okay, this is important. So really basic. You have two equations and you can do everything with these equations. Try to understand what they are. Okay. That's all for today. Thank you for your attendance. Take care of yourselves, guys. See you. Okay. Bye-bye. Have a good weekend.